Hi, everybody. Thank you for attending my presentation. My name is Amine Barrak. I'm currently a PhD candidate at Polytechnique Montreal. Today, I will present my paper entitled On the Co-Evolution of Machine Learning Pipeline and Source Code. It's an empirical study of DVC projects. So what is a typical machine learning pipeline in machine learning projects? First time a machine learning pipeline was introduced by Microsoft team members where they show a series of steps chained together to form the machine learning workflow essential stage. This stage include data and models-oriented artifacts, starting from data collection, data cleaning, until the model evaluation and model deployment. This stage constructs a machine learning pipeline. Let's start by an example of machine learning project. We consider that the machine learning project can have three artifacts: code, data, and models. We can see that these artifacts evolve separately and they might have different versions. Also, a snapshot of the projects may contain different versions of these artifacts that are compatible to work together. We need a way to keep tracking the different versions of these artifacts and also a way to reverse the previous snapshot of the projects, including a compatible version of these artifacts. So the question here, how can we keep tracking these artifacts together? We know that Git can store and version code, but it doesn't handle storing scalable large files or models. ML flow actually and PyCharm and the DVC, and DVC are tools to make a machine learning pipeline are tools to make a machine learning pipeline traceable actually. Yeah, we choose a DVC pipeline specifically because since it is lightweight and work as a layer with GitHub. It also supports non-machine learning projects. So as we said, GitHub can handle source code artifacts, but cannot handle scalable models and large data set. So here it came the DVC that works as a top layer, as we said on GitHub, by making pointers to large files dataset and machine learning models using MD5 checksum. This is an example of a DVC file. It looks like a source code file. It contains the checksum to link the actual stage with its dependency. A DVC stores the pipeline evolution starting from data collection to the prediction models. So our study came here to understand the process of the co-evolution between these three artifacts: the source code, the data, and the models. We designed our three research questions. The first research question: how common is the usage of DVC in GitHub projects? The second research question: how common coupling exists between software artifacts and DVC artifacts? The third research question: how does the complexity of the DVC machine learning pipeline evolve over time? Our first research question is to look for how common is the users of DVC in GitHub projects. To do so, we ran an advanced search on GitHub looking for the DVC project to find out how current the machine learning versioning tool like DVC are used in open source projects, and how much do the projects rely to these tools. As a result, the first plot shows how quickly projects adopt DVC after creating their repository. We found out that there is a quick adoption of DVC after creating the repository. There is 350 projects that adopted DVC for less than a month. The second plot shows how long the usage of DVC in projects. We found that 25% of projects applied DVC for more than a week. On this plot, we compute the proportion of changed DVC files chronologically in the projects. We find that 50% or more of DVC files in a project are changed at least once every 1/10 of a project's lifetime. which means that the DVC files are frequently changed in the project lifetime. And the last plot shows the remote storage used by DVC project. There is 127 of the project have no trace of their DVC remote in the GitHub repository. This is due of a toy project with a usage of less than a day. And there is also some projects were hiding their configuration file for security purposes. And the three top used data storage location, there is the Amazon with 85 projects, and others were using cache local files. There was 78 projects, and Google Cloud Storage with 35 projects. Here is our second research question. To respond to this research question, we filter out the most active project to compute the coupling at the commit level, and for the pull request level, we kept only project having at least 10 pull requests. After that, we classify all the files on these projects to the DVC artifacts files, including data pipeline utilities and source code artifacts, including source, test, data, and git ignore. Using the association rules, we were able to compute the coupling, and we used the chi-square test to validate the analyzed coupling. The reason of computing the coupling is analyze the required maintenance and efforts that the developers are should have, like and the effort actually to add or change data models files and the machine learning pipeline specification in a project during a regular development. At this level, we studied the coupling on the commit and pull request level between DVC and between the DVC artifacts and source code artifacts. We show here only the coupling between the DVC pipeline and source code artifacts on the pull request level. Having this plot includes, as we say, the pull request level 10. It includes only 10 projects having at least 10 pull requests. So the rest of the coupling results can be found on the paper. As we see here, 1 out of 4 pull requests changing source code require a change to DVC files, and 1 out of 2 pull request changing tests require changes to DVC pipeline files. And here there is 80% of cases where we have a change data file require a change to DVC pipeline files inside the pull request. So we can talk about previous studies that have shown that source code and build code evolve in terms of complexity and size. Moreover, since we find a high change frequency in the DVC files in RQ1 and a high coupling between the DVC and source code artifacts in RQ2, we aim to explore in the third research question how the complexity of the machine learning pipeline evolved over time. As we can see, this is an example of a DVC stage and how the pipeline is shown on a graph form with its different dependencies. We will use 2 metrics to compute the complexity. The first metric is the McCabe complexity. It is used to estimate the graph structure complexity of the pipeline. We compute it from the number of edges and nodes in the pipeline. The second metric is the Halstead complexity. It is used to reveal the file. Excuse me. So the second metric is the Halstead complexity to reveal the file's verbosity and effort to understand actually the textual form of a DVC pipeline files. We compute it using the operator and operands. So the operators are the comments in top level, and the operands are the parameters passed to the operators. To do so, we reproduce the pipelines of the 25 most active projects and compute the two metrics complexity. As a result, we compute the Halstead and McCabe complexity for each project, and we didn't find a common evolution trend. We classify the complexity trends to increasing, fluctuating, major impact, and sudden drop of the trend of the complexity. And here we can see that we have some example of the complexity evolution that we find here in the McCabe. We see that it's fluctuating, and here it's an increasing trend. Same here on the complexity of Halstead. We can see here same project react with a different manner. In the Halstead complexity, it was an increasing. However, it was here, same project, it was fluctuating. So in the McCabe complexity, we found 6 projects have an increasing trend and 5 projects have a high fluctuation. However, on the Halstead, we found 7 projects have an increasing trend and 7 projects have a high fluctuation. So what to do now? There is some implication that we come out in a paper. First implication is it's for the machine learning developers. There is some advices that we gave to the developers. For example, how to use properly the remote storage, not save the files to GitHub. Instead of that, you can use the Amazon, for example, storage, and use one DVC stage per similar data folder. For example, it's not proper to make a DVC stage for each data files, like examples, the images. You put them all in one folder and use the DVC to point to this data set. And split pipelines, for example, into subcomponents, it's better to facilitate the maintenance and reduce the pipeline complexity, because subcomponents, it's less complex in the pipeline and easy to maintain it. Other application is for the developers. For example, one notebook cannot it's actually can contain different stage of the pipeline. It can even include all the pipeline in one notebook, and the actual version of DVC is not handling the different cells inside the notebook. So it is something for future work on and advices to developers. Also, an application to researchers when there is a lack actually of techniques or tools that can assist developer to identify code changes that require DVC maintenance. For example, fixing a bug in the pipeline. There is a lack of tools to automate this kind of fixing. So as a summary to our presentation, first, we show how DVC is a layer on the top of GitHub and how to make pointers to the data and models. Second, we show how the DVC is showing a high change frequency in DVC files in RQ1 despite its young practice. Third, we show how the DVC has a high coupling with the source code artifacts in the pull request level. It's shown on RQ2. And finally, the complexity trend evolution of the machine learning pipeline. Thank you for attending the presentation.